University. A person joins with a history major to study physics. And we always wondered, why? What is he doing? And he said, look, I was studying history because I wanted to know what is the past, what occurred. But he went further and further in the past in history. He found that he cannot go beyond maybe 4,000 years, paleontology, maybe 10,000. He wanted to go even beyond. Then he felt the only way is to go to the beginning of the universe, the Big Bang theory. And so he went to physics, but he had enough knowledge of mathematics to be able to make this transition. The university took him for PhD in physics. That is Princeton for you. But what happened is he started developing mathematics to learn more of physics. For the mathematics that he developed, he got a Fields Medal. Now, the theory that he developed for the origin of the universe and Big Bang and evolution, it is called string theory. It is started by someone called Eric Lander. Sorry, I made a mistake. Edward Witten. Ed Witten. Eric Lander was the biologist, mathematician and biologist. Edward Witten started string theory. Right? He was a history major, shifted to physics. Now, history in India, I am talking about as a major subject. People don't take. Students who didn't get anything else go to history. This is very unfortunate. Again, I come back to my institution that is familiar. At Princeton University, they have taken the statistics of last 100 years, which is the major that is opted for the top 5% of the students that are coming in. They find that half of the top 5% opts for history as a major. And people have looked at, the university authorities have seen where they end up with. After history, they go on either to do a PhD in history or a business management degree or a law degree and gets into jobs, and finally, 30 years after their degrees or 40 years, they end up as chief executive officers of multinational corporations, large multinational corporations. And why are they reaching there? When you are talking about history and learning history seriously, they look at the past 10 years, 50 years, 100 years, and can analyze the events in a very objective way to see why things have changed the way it has. It gives them a knowledge to be able to predict what could be the next 10 years, 30 years, 50 years for an organization. By such objective analysis of what has happened in the past, they are visionaries in many ways. From history they have learned. Our problem is that the people who went into history are people who didn't really have the aptitude for it. We don't have good visionaries. Good visionaries will come when people follow their subjects of interest, not what the society or the parents or the teachers or your neighbors or your classmates tell you. It is a luxury to be able to do what one likes to do. In a developing country, there is always the concern, if my son or daughter takes anything other than computer science, will they get jobs? It was true maybe 20 years ago. It is true maybe to some extent now. But even those parents who could afford without any worry their children studying what they like to do, even those parents do not allow the children to take what they want to take. They enforce, you take computer science or you take medicine. Nothing else. If we, I tell you an inner, data that is there. Every year, 3 or 4 computer science or IT workers who are earning 7 or 8 times that of the professor's salary of IISc, after having worked in institutions like TCS or Infosys or Wipro or any other, they resign the job, 3 or 4 people only, and come back for doing a PhD. They say, yes, the salary is about 1.5 crore, so much more than a professor, but we cannot do this anymore. It is dull. It is not what I wanted to do. I wanted to do something else. There are, of course, people there working because they like it, but there are large number of them working because that's the job they got, because that is what they are forced to study in the beginning itself. For each of these 2 or 3 or 4 that has come out, there are hundreds of others who would like to come out but do not have the courage to throw away a very high paying job and stay the whole life doing that. It's a pity. I say all this because I wish Rataya Garu was here so that he would open up the whole system. But maybe some of you could tell that there is a possibility, without making much changes, challenge Shivanadar University and ahead of them. I told the story of the historian becoming a physician, Edward Witten. So there is a custom at Princeton University again. Just as you would in future talk about Vijnan all your life, I talk about my institution. In the convocation, a student is given 3 minutes to speak, the best student of the batch. In the convocation, you are not just going and getting the degree and leaving. 3 minutes was assigned for the best student in the batch to give a talk. It's called a valedictorian's address, bidding farewell. I had a master's from Princeton. By the time I got my PhD, I received it in absentia. But in my master's degree, I was attending the convocation, and the valedictorian, an undergraduate student, was talking in 3 minutes. He said, my experience in Princeton, the first day when I came, I found there are lots of squirrels in the campus. They were all black squirrels, without the line on the top. We used to joke that Sri Rama didn't visit that area. But he said all squirrels in Princeton was black. By the time he got to his second year, he said some squirrels are black. Third year he was not sure. Fourth year, at the podium, he was taking the degree. He said, look there. He pointed out, I see a squirrel. The only thing that I know about that squirrel is that on this side of that squirrel at this moment is black. Everything else is uncertain. See the transformation. He said, 4 years of the degree, this is what has told me to be skeptical of everything, to be uncertain about everything. I will say, yes, that squirrel right now on this side is black. Rest I have to find out. That is the education he received in Princeton in 4 years. To be able to question anything. Our early specialization is just against all of that. Any attempt at exploring beyond that little area will be discouraged. It doesn't exist. It will not be attempted. The reverse should be the role of education, to be able to question everything, right? I say this with confidence in Vijnan because there is a possibility. I feel that there is a possibility to change the system following the new education policy. I was, just trying to see. Children really ask questions which are difficult, sometimes impossible. I had an early question. When I was a first year BSc student, I had an excellent teacher of inorganic chemistry, an outstanding one, Shankarayar his name was. We are talking about 1968, okay, my first year BSc. And the question was asked in a very casual way. He was teaching, this was in University College Trivandrum, right? This was at 66. We had the Cotton and Wilkinson's brand new textbook has come. It was a big revolution in 66. This was 68, 69 first year. And the teacher was talking about this sp3 hybridization and diamond, sp2 hybridization benzene, naphthalene, anthracene, and graphite. Graphene didn't exist, right? And the teacher finished the class and he was going out. And I was kind of curious. I ran behind him and said, "Is there anything like this for boron?" Very casual question. I had no idea. He was talking about carbon, methane to diamond, benzene to graphite. And I said, "Is there anything like this for boron?" He said, "Okay, let us look at." So we went to Cotton and Wilkinson's inorganic chemistry. It doesn't talk about allotropes of boron. It talks about boranes, but not much. I went to IIT Kanpur for MSc, and I asked the same question. There was Professor P.T. Manohar and Animesh Chakravarti. They all said, "Well, no, I don't think there is, we don't really have this." So I went on to do my PhD, and I thought I will work on this, But you see, in professors, I show this. Professors are like this. You go as a PhD student. I am going to research whatever I want. A new graduate student coming in. He goes with the professor, and then professor says, "Well, you have to do this." So I am going to research whatever my professor wants, because I didn't have any specific question. Then I get a job, and I am running around. I am doing whatever my tenure committee wants. To get the job permanent. And here I say, okay, the grant committee wants, so I will do that. And when I am about to finish, I say, I am now going to do what I want, but often it is too late. The reason I am saying is that you should have questions. You should have questions early on. You should have questions early on, and at least keep it with you. It is not automatic. At Princeton Chemistry Department, they do the following trick. PhD thesis doesn't have to be defended, because there is a PhD exam committee. They monitor you every 6 months, and you are making progress, you are publishing, there are no second thoughts about your degree. But along with the PhD thesis, one has to submit 3 research proposals which are not connected with one's thesis nor with the professor's subject. So we have 3 research proposals, and those research proposals have to be defended. That is the PhD thesis defense, not the thesis itself. The good thing is that we have 3 research proposals which is our own. Right? So I talked about some boron thing along with it, one of them. So I had 3 research proposals. One was experimental, which I didn't do. The other 2 I did. The first of my publications from my first job from the University of Hyderabad was one of the research proposals. Actually, this is the topic. Now, the original question that I had, is there something like this for boron? Only partial answers I got in 2000, 2001. I stayed on for 30 years with this question. I still continue with that question. But you cannot wait for 30 years for an answer, because you will not get a job. Right? But you keep thinking about it. I did many other things, and those many other things, over the years, there were different philosophy for what I want to do. I started looking at connections between different areas: organic and organometallic chemistry, chemistry of various main group elements, all kinds of things, but not one problem. An idea that can connect across. So when I say this, it's very vague. It is not like the theoretician's operator and there is a result. I mean, many things that were tried. Like I say hydrogen bond and other weak interactions, for example. So what I did was I looked at hydrogen bonds and I found that usually when we have XHY as hydrogen bond, the XH bond becomes weaker and the new part is formed. But if you look at very weak hydrogen bonds, the XH bond becomes stronger. And we thought maybe we should look at weak interactions in all the main group elements. And we found that in every one of these main group elements also we have the same possibility. Some bonds at a very weak stage could be stronger by forming a weak interaction. Then we said, how about transition metals? Are they able to form weak interactions of the hydrogen bond kind? Not even one available. And we looked at why that is so. In other words, when I say one looks at generalizations, it is looking across the periodic table. Well, this is just a list of projects that are connected. That is being done right now. But it's not important as such. But these are not isolated projects. Projects done for a particular reason. And the last one I have listed, compounds or clusters of an element to its allotropes. That's the topic that I was talking about. So the old question that I had, is there anything like this for boron? It gets refined as years go by. Yeah. So basically, I try to refine this question. How do you have an equivalent of methane to diamond and benzene to graphite? Right? And now I try to get a more systematic way to this answer. Right? I say the boron chemistry can be divided into three parts. One, this is a mistake, analogous to carbon, right? Chemistry analogous to carbon. Then polyhedral boranes and 2D boron. Analogous to carbon, it is easy. CH3 plus, there is BH3, CH4, there is BH4 minus, and so on. All of borate chemistry, NH3, BH3, frustrated Lewis acid, anything that you think of normally is a chemistry of boron analogous to carbon, right? They are very important, there is no question. But, important enough for a Nobel Prize to be given for hydroboration alone. But let me get to the next part. The next part is polyhedral boranes, very interesting part, icosahedral borane, all -2 charge species. Wade's rule which says this. Inorganic chemistry textbooks would have this. There is even a simple way of justifying the Wade's and +1 skeletal electron pair rule. There is a Rudolph diagram in almost all of the inorganic chemistry textbooks. So there is this diagram, right? So there is a lot of polyhedral borane chemistry known. And what is this diagram? Some of you, those who are doing MSc inorganic chemistry, would have reached that far. BSc chemistry, well, some courses might have touched upon this. B12 H12 2 minus, B11 H11 2 minus, and so on. Icosahedron, if you remove one vertex, you get B11 H11 minus 4. This is a nido structure. This is called a closo. It's a closed kind of structure, and so on. And this will be an arachno where it will be -6. So there is this structure that is available from 76. It's there in any inorganic chemistry textbook. This is the Rudolph diagram. I have drawn it again. There is a Nobel Prize given to Lipscomb just for studying polyhedral boranes experimentally and computationally. Now, I am trying hard to do this idea. How do we connect like methane to diamond or benzene to graphite, right? What is the equivalent of benzene in the polyhedral, in boron chemistry? It looks as though B12, H12 minus, the icosahedral borane dianion, that might be the most stable one, right? Perhaps we should begin with that to make elemental boron. This was the thought. And when you look at the literature, alpha rhombohedral boron, which is not the thermodynamically most stable allotrope, is already there in textbooks, except the structure is not explained well enough. If you look at this, it's as if, see, in elemental boron, there are no hydrogens. So all B12s have lost the hydrogens, right? And then you are putting together B12 icosahedra. Now, if you consider 3 icosahedra brought together like this, there is a BH that is not there anymore, there is another BH, third BH. 3 orbitals are there. When you have 3 orbitals, we have seen it with H3. We need only 2 electrons because the third, the degenerate combinations of the orbitals are higher in energy. We need to only take this. Now that, I remind you again, see, we have 3 orbitals coming together. The degenerate higher lying ones need not be filled. They are not bonding. So here we have something very interesting. We need to have -2 charge. B12, H12 has to be -2. When you share, 3 orbitals, we need only 2 electrons. So we have 1 electron extra. That 1 electron extra is shared by 3 polyhedra, which means that each one gets 1 by 3. But then we have such connections from 6 other atoms here. See, the middle 3-membered ring and the one that is below, those 3 are connected to B12 above and below by 2 center 2 electron bonds. So we don't gain anything, lose anything. But here we have 6 of them, each giving this 1/3 electron back. So we have 2 electrons saved. And so each B12 is having the -2 charge in alpha rhombohedral boron. So we have a connection. This is the easy connection. It is there in textbooks. But thermodynamically most stable allotrope is far more complex, and that is the beta rhombohedral boron. Now this is a tough problem. Only those who listen carefully can get it, otherwise it will go past you. But I will still attempt, right? In the process of getting there, I must say we have new electron counting rules, which even comes in CSIR JRF exams occasionally, right? So let me begin this way. We have benzene, naphthalene, anthracene, Huckel for n+2 pi electron rule. We have Wade's rules, which says for a polyhedral borane that has to be n+1 skeletal electron pairs, where n is the vertex number, right? Number of vertices. Each BH gives 2 electrons because BH boron has 3 valence electrons, and formation of the BH bond, 1 electron is gone, so we have 2 electrons. And so B12 H12 2 minus means n is 12, n+1 means 2 electrons here would make that extra lone pair, so n+1 skeletal electron pair. But if you were to put together icosahedra, like we have benzene, when you put together it is just edge sharing, there is nothing more. Here we can have sharing of 4 boron atoms or 3 boron atoms and so on. So you have endless possibilities. For this we had introduced a new electron counting rule, and we call it MNO rule, and I'll tell you why is it so. Let us look at an icosahedron connected with another icosahedron with a 3-atom sharing, which means that the 3 hydrogens from both the icosahedra are removed, and we have the triangular phase sharing. In Wade's rule it was n plus 1. N was the number of vertices. Here we have an additional variable. That 1 was changed into a variable m, because for MNO we have more than one polyhedra. So here the number of polyhedra is 2, right? We see 2 polyhedra, so it is m equal to the number of vertices. It is 2 icosahedron. Each icosahedron has 12 atoms, right? But 3 of them are shared. So instead of 24, 12 plus 12, we have 3 atoms, 3 vertices less, because the triangular face is shared. So we have only 21 vertices. And of course this O is a special case where the bridging is with one atom alone, right? So that is not applicable here. So O is 0. So we should have 23 electron pairs here, according to this rule. Now if you count the number of electron pairs, we know each BH gives 1 electron pair, and we have B21, H18. If you count the total number of groups, here it is BH 18 times and 3 boron atoms. Now 18 BH gives 18 electron pairs, and there are 3 boron atoms in the middle. Each boron brings 3 valence electrons, right? 3 into 3, 9 valence electrons, right? Which means we have only 4.5 electron pairs, right? So 22.5 electron pairs only we will have, but we require 23, which means that half an electron pair, which means 1 electron has to be added as a charge. So if B21 H18 were to be made, it will be an anion. Now when this was being published, it was not known. But 7 years later, this is made. Complex structure, B21 H18, and it is found to be an anion. And there are reactions of it as well, right? So there is some justification for something like this. Of course, you can build on this into naphthalene, anthracene, and phenandrine, and so on. Similarly, we have all these possibilities. A lot of boron chemistry yet to be discovered. But surprisingly, in literature, there was one X-ray structure of B20H16 where four atoms are shared of the polyhedron, and this was made by Lipscomb and Mittertis more than 50 years ago. They got the X-ray structure, right? Much before he got the Nobel Prize, Lipscomb. They got the X-ray structure, everything was fine, but they were so obsessed with the dianion polyhedron that and Wade's rule, they felt this is an exception. They didn't want to even consider it further. They published a communication, left it there, exception. Imagine that. The influence of the Rudolph diagram and the dianionic polyhedron boranes prevented them from exploring this further. Now, but if you look at this, it is m is equal to n is equal to 20. It has to be neutral, and it is. Right? So there is a lot of chemistry that could have been discovered even earlier, but people didn't follow it up. Imagine that if you take icosahedra, there are this many ways of putting them together, and of course one is knocking a vertex away, that is the Nido structure. Now if you take any one of them, then we have so many possibilities of Nido. If you take any one of them, there is still so many possibilities. In other words, the condensed benzenoid aromatic equivalent in borane chemistry is infinitely more complex, and several isolated ones among these are known, not many. Right? Now this is all starting with just one polyhedral borane, icosahedral. Remember, we had this many of them. With any one of them, this kind of a structure is possible. So the variety of boron chemistry that is available is really incredible. It's just that we are at 100 years ago what carbon chemistry was. The MNO rule is there in many of these textbooks. and that is what prompts occasionally CSIR exams to put them. Now, beta-rhombohedral boron is far more complex. Now, I will venture with this. If only one is very careful, one would make sense out of it. Otherwise, it will be a waste. So let me try. We start with an icosahedron. The idea is somehow to make as many icosahedra as possible in the structure, because icosahedral boranes are the most stable arrangement in boron chemistry. Why is icosahedral borane the most stable one? That question itself can be asked, and there is a very interesting answer, but that will take another 20 minutes, so I will leave it. It is available in a review that I had indicated in the very beginning, Orbital Interactions in Chemistry, Israel Journal of Chemistry 2022. But let me begin here. Icosahedral B12. Instead of, ideally one should just make icosahedra connected to another icosahedra 12 times and continue. But that does not make a translational symmetry based space filling model. So what nature has done is that in beta-rhombohedral boron, which has 105 atoms, and I say in the idealized unit cell. Idealized because experimentally we don't have the idealized unit cell, right? That is the complexity why people couldn't make sense out of it for a long time. What nature has done is one begins with B12, and instead of connecting to another icosahedra, it cuts it into middle. Half of an icosahedron, as you would notice, half of an icosahedron, this part is a pentagonal pyramid, the top part is also a pentagonal pyramid. Right? Two pentagonal pyramids put together is an icosahedron. Right? So if you have an icosahedron connected, you could of course connect with half icosahedra, that is pentagonal pyramids, to all of them. I indicate initially the peripheral 6 boron atoms. So that looks like this. Right? What we have is a pentagonal pyramid, another one, and so on. If we now connect all of these boron atoms with the pentagonal pyramids, we get something which from a distance looks like C60. Actually it is symmetrically that one, because you see here a 5-membered ring, another 5-membered ring, and so on. There will be 12 5-membered rings. C60 has 12 5-membered rings. It also had how many 6-membered rings? You can count 20. Now what I would like to say is that this is like C60. In fact, it is the outside surface is B60 because there are 12 5-membered rings, 12 into 5. So this is B60, except below each 5-membered ring we have one atom. Right? Below each 5-membered ring we have one atom. So we have 12 such atoms. Right? So that is this 12 just below the 5-membered ring. I have set B12 inside B60. But these 12 individual boron atoms are connected to the central B12. So this is like a B12, which is the central B12. It is connected to another 12 boron atoms, which are these boron atoms, and outside is the outside the B60. This is one of the building blocks of the beta-rhombohedral boron. It becomes more complex, but slowly I go through the description at least. Now, if you want to have all of these 5-membered rings into B12, one way is to bring two of these together. If I have a B84, see this is B84 now, 12 plus 12 plus 60. If I bring one B84 on the top of another B84, then one pentagonal pyramid and another pentagonal pyramid from the next one comes together and we have an icosahedron. Right? But this being so large, we can bring only 6 of these B84 around the central B84, which means that it can do this it can do this 6 times. So the remaining 6 pentagonal pyramids have to still find some other way. The unit cell is large. It has a B10 unit in addition. Now this B10 unit is also quite interesting. It has a central atom, and with respect to that central atom, it's a pentagonal pyramid here. Now one 5-membered ring and an atom behind. Now this atom is shared by another 5-membered ring on the same side. So that is another pentagonal pyramid, and the same thing on this side as well. So we have 3 pentagonal pyramids if you look from these slides. So if I were to put this on the top of a B84, you essentially generate one icosahedra. I can put another here and there, so there is yet another one. So it becomes complex. Yes, so we have a B84, another B84, a third B84 around a B10. Now this is not the completion of the structure. If we connect a large unit like this to another one of the same kind through a single boron atom, and it is not easy to represent. So what I have done is I cut this out, right? The B10 along with this pentagonal pyramid and the pentagonal pyramid here and the pentagonal pyramid here. The pentagonal pyramid is 6 atoms, 6 plus 6 plus 6, 18 plus 10, 28. If I take this 28 atom unit and connect to another 28 atom unit through a single atom, 28 plus 28 is 56 plus 1 boron, right? 57. And that unit is indicated on the side here. So I am only describing the idealized unit cell. The idealized unit cell is not good enough. I would say idealized unit cell is B105. We can treat it as either B84, B10, BB10 or B48 and so on. The idealized unit cell acts as though it requires more electrons than what is available. We can divide it as 4B12 and a B57. What is meant by this? 4B12 because we have a B12 inside and we have another B12 here. And if you take the number of B12s in 105 atoms, we will have something like 4 B12s and a B57. Well, this is a schematic representation. We have the B10, B84, B84, B84. This B84 is connected to 3 of them and another 3 here. And this B10 is connected to another B10 through a single boron atom. So we have 4 B12 and a B57. B57 is B28, B28. B12 will be B12 H12 2 minus equivalent. So 4 B12s require minus 2 electrons. And how many electrons does this square? There we have to use MNO rule and get this one. And we find that it has 3 extra electrons. So we come back and say that this is plus 3 and this is minus 8. So we should have B105 minus 5 because this is minus 8 and plus 3. But elemental boron has to be neutral. This minus 5 is not acceptable. If you calculate the neutral idealized unit cell structure, it looks as though it is a metal because it requires these 5 electrons. And I will cut this short by saying those 5 electrons are given by extra boron atoms that are present in addition to the unit cell, idealized unit cell. Each experiment produces these extra atoms in different places. So each experiment gives a new result. Right? This is approximating the problem, and I will stop at this stage because I see that I have kind of tired most of you out. This is an attempt at giving different extremes of examples, starting with a vinyl cation rearrangement through 3-membered rings to borophytes, borophenes, then coming back to the elemental boron problem and so on. I have a full talk which will continue with this. I will just get through this to the end. Well, I have to thank Pathaya Garu for this kind invitation, and of course all of you from the faculty of the Department of Chemistry. I thank my own department, which has been very kind, which allows me to continue as long as I want, where retirement is not an issue. Our computing facility which has helped me, and the CRB which has given me a position to continue. Many students, postdocs, UG and MSc students worked on these things, and I really should say that it is their result. And my current group, I have 2 postdocs and 2 PhD students. They will all be leaving soon. And I finally thank you all for sitting through this and giving this opportunity. Welcome to IISc Bangalore. Thank you.